Hi, welcome back to this video series on quadratic residues of composite numbers. Today I will apply the concepts of quadratic residues and construct a crypto system. Okay, this crypto system was invented back in 1980s based on the hardness assumption of quadratic residue in a composite group. I have talked about the foundation of quadratic residues in all the previous 6 segments. So today I will bring the concepts into a crypto system. Okay, so the crypto system that I will talk about today is called Goldwasser-Micali encryption system. This is the very first probabilistic encryption system published after RSA was published. RSA was based on the assumption that it is difficult to factor composite numbers made of large primes. There may be other ways to break RSA without factoring, but we don't know yet. But here, in the case of the Goldwasser-Micali encryption, the assumption is that it is not only hard to factor a composite number, but it is also not easy to distinguish whether a number is a quadratic residue or not in a composite group. So we will be looking into how to design a crypto system based on this assumption. So let's take our two communicating parties, Alice, right? Alice is here and Bob is here. So Alice wants to send a message to Bob using the idea of quadratic residue, but I will explain it very briefly first before we get into the details. Let's assume Alice wants to send a message to Bob, right? And the message, for simplicity, is made of only bit 0 or 1, okay? So Alice will either want to send 0 or 1. If we can securely send a 0 or 1, then you could, in theory, send any message, right? Because everything is made of zeros and ones in any case. Okay, so the goal is to send a 0 or a 1, right? Either a 0 or a 1. That's the message space, if you want to call that way. So how do we send this message from Alice to Bob without being sort of eavesdropped by an eavesdropper? The eavesdropper, of course, will see the ciphertext, but it must be difficult for the eavesdropper to confirm that the message is 0 or 1. Okay, he can make a rough guess, but that's like a half probability, right? So we wanted to be able to have a crypto system in which the eavesdropper cannot make a guess significantly better than 0.5. Okay, that's basically what we are going to talk about. So the idea is pretty neat. So what if we use the notion of quadratic residue to encode this 0 or 1 possibility? If the message is a quadratic residue, let's say Alice wants to send a 0, maybe Alice can send a quadratic residue to Bob. Bob will be able to test quadratic residue or not because he knows the prime factors. Suppose Alice wants to send 1, she will pick a non-quadratic residue. Bob will also be able to test that because Bob has the prime factors. Okay, so that's basically the idea. So what will Bob do first? Bob has to create 2 primes P and Q. They are secret primes. He doesn't show to anybody, right? And he multiplies them to form a new number n, right? N is P times Q. And he publishes n to the world, so everybody knows the n. But it's difficult to find P and Q from n. That's the assumption. In this context of this Goldwasser-Micali encryption, there is one more argument needed for Bob. Bob should actually generate a number called z. It must have an interesting property. It must be having the Jacobi symbol j to be 1. Okay, this property is very important. And Jacobi of, if you want to call it Legendre symbol, that's also fine. Now Legendre of z, right, over p must be -1. That means z is not a quadratic residue in z star p. And similarly, the Legendre symbol for we talked about Legendre symbol earlier, so it's the same thing. Okay, over q is also -1. Now if you multiply -1 and -1, you get the Jacobi symbol 1. Okay, so Bob has to generate PQ. That's the most important one, right? First step. And then he has to generate a number Z with the property that the Jacobi symbol is 1. Okay. So what is public key then? Public key is basically two things, N and the Z. Alice wants to send a message, right? It can be either 0 or 1. So what will she do? She is doing this nice trick now. She's going to pick a random number X. Okay. Where does this random number come from? This random number X come from the group Zn star, because N is public. So she will use the Zn star group, multiplicative group Zn star. Suppose she wants to send a message M to Bob. What she does is she computes Z power M. Where is this Z coming from? This Z, remember, is public. So this is public and this is public, right? N and Z are public. Therefore, Alice will just take Bob's public Z, raise it to her message M she wants to send. But here comes the neat trick. She multiplies that by the X square, the X that she just picked randomly. Okay, so this is basically the crypto system. Alice computes Z power M times X square mod N and send it to Bob. So Bob gets the C, right? C is the ciphertext. The question now is, how can Bob check, or what can Bob check to figure out the message was 0 or 1? So now we can apply all our Legendre symbol discussion and Jacobi symbol discussion. Okay, let's consider the possibility. So message can be either 0 or 1, right? Those are the only two possibilities. But how can Bob confirm what was sent by Alice? So let's pretend for a minute that the message M is 0. So what can you say about C then? C becomes just C is equal to X square, right? If M is 0, okay, what can you say about the message C? C that Bob gets must be X square. But Bob doesn't know X either, right? X is private to Alice, okay? And that's something I must said. X is not public, X is private, and it's unique for each message. That's something I will talk about again later. So what can Bob do with the C? Bob can now check whether C is a quadratic residue or not, because he knows the prime factors P and Q, okay? Since he knows the prime factors P and Q, if the Legendre symbol of, well, you can just apply the Jacobi symbol. In fact, Bob basically computes Jacobi symbol on C, right? Which will be 1 because it's a quadratic residue, but even Eve can do this, but that's not enough, right? So we should not just use Jacobi symbol, of course. So we should be using the Legendre symbol, right? Legendre symbol on the ciphertext C with P, for example. Okay, if this is 1, what can we say? If this is 1, we know for sure that the message or the ciphertext Bob received is basically an encoding of message 0, because otherwise C equal X square wouldn't be sent. Okay, and of course Bob also have to do Legendre symbol of C in group Q, right? Okay, it has to be also 1. Okay, so now Bob knows for sure that Alice and M equal to 0, because he computed the Legendre symbol using the incoming ciphertext C, uses the P and the Q which are private, and if the Legendre symbol says the answer is 1 and 1, then he knows, yep, the message M must be equal to 0. So he confirmed it. Okay, now let's consider the other case. What if the message Alice sent is M equal to 1? So in that case, what will be the structure of C? So let me now erase this drawing. Okay, so let's consider the scenario that Alice has picked M equal to 1. So in that case, C will be Z times X square, right? Okay, C times X square. Remember that now comes the interesting property about Z. Okay, what is Z? I mentioned earlier, Z is a public key picked by Bob, but Z itself is not a quadratic residue. Okay, it is not a quadratic residue, and the Jacobi symbol of Z is actually +1. So that's something very important. I will talk about it a little bit later, but Jacobi is also 1 for the Z. Okay, now Alice is sending Z times x squared to Bob, so it comes to the side. What is Bob going to do? Bob is going to do exactly the same. He's going to compute legendre symbol of the incoming ciphertext C, applying it to P. Okay, what can that be? It has to be -1. Why? Because this is not a quadratic residue, right? It's not a quadratic residue, and this is a quadratic residue. This part is a quadratic residue. So if you multiply a non-quadratic residue with a quadratic residue, what you get is a non-quadratic residue. Okay, that's something we talked about earlier. Therefore, Bob knows that the message Alice sent must have been m equal to 1. Okay, so why can't eavesdropper conclude that? Eavesdropper can't conclude that because eavesdropper cannot compute the legendre symbol on the incoming ciphertext C because he doesn't have P and Q. So remember, to compute legendre symbol, we would need P and Q. P and Q are private. Okay, and if the hardness assumption is it's difficult to predict P and Q from N, therefore the ciphertext C cannot be analyzed by the eavesdropper because he doesn't know P and Q. So on the other hand, Bob can successfully analyze it because he knows P and Q. Therefore, he can conclude that ciphertext C is not a quadratic residue. That means the message M must have been 1. Okay. So that's the key idea behind this crypto system. So to summarize it, Bob generates a private key P and Q. He multiplies that. He publishes N, which is the public key. So N is the public key. But in addition to that, Bob also computes something called Jacobi symbol on a number Z to make sure that Jacobi symbol is 1. And moreover, the legendre symbol for Z is -1, both in P and Q, mod P and mod Q. We talked about legendre symbol, Jacobi, so I'm not talking about again and again. So with that condition, he publishes now N and Z to the world. This is the public part. And Alice, she picks an X randomly. This is a private part. Okay, she doesn't expose this to anybody. But what she's going to do is she uses Bob's public key, right, Z, and writes to her message M and multiply it by x square and send this ciphertext C to Bob. Bob will now check whether the incoming ciphertext has a legendre symbol value 1. If it is 1, he concludes the message must have been 0. Otherwise, the message must have been 1. That's how this system is organized. Okay, with that brief background, I will now show you a simple demo of this particular crypto system. And the probabilistic part is built in here. Suppose you send the same message. Let's assume Alice sends the same message M equal to 0 to Bob 2 times. The ciphertext will be different because every time a message is sent, Alice has to pick a new random X. Therefore, ciphertext will be different. That's the key part, which is not present in the first version of RSA. Which RSA is not a probabilistic encryption when it was invented. Later, people added padding and standards have evolved, but the original publication, it's fixed for encryption. But in this Goldwasser-Micali system, it's probabilistic because we are choosing a random number X every time we send a message. Okay, and the message itself is either 0 or 1. 0 is encoded using a quadratic residue. 1 is encoded using a non-quadratic residue. That's basically that's the reason why it's raised to power M, right? M is the message we want to send. Z itself is basically a non-quadratic number with the Jacobi value 1 and the legendre symbol -1 in both P and Q. Okay, that is basically the core idea. And the eavesdropper cannot break this system with the assumption that factoring is hard, because the eavesdropper cannot compute the legendre symbol because he doesn't have P and Q. The legendre symbol computation requires, in this case, if you are working with a composite number and the prime factors. We don't have any polynomial time algorithm that can check whether a given number is a quadratic residue or not. Okay, that's where the hardness assumption is built in this crypto system. Okay, so the algorithm itself is not so complicated, but I would warn you that my implementation is just very basic implementation, not necessarily ready for production, right? It doesn't have it doesn't have controls against timing attacks and so on. So that's not something I bothered at this point. So as I mentioned earlier, key per generation is extremely simple. We generate two keys P and Q, private keys, and then you multiply them to form a public number n, public key is n, and then the Z itself is an element in Z is an element in Z star n, right? And it must also have a property that the Jacobi symbol is -1 in mod P and in mod Q. That's basically the Jacobi symbol we talked about earlier, right? That's another important fact. And then we return to the caller n, z, p, q. Okay, n and z are public, p and q are private, just to be clear. Okay, and now encryption. So how are we going to encrypt? We randomly generate a group element from z and star, and then we do z power m times x square mod n. That's what I explained in the algorithm. And the decryption part goes like this. Incoming ciphertext is evaluated. The Jacobi of the system is evaluated, right? If the Jacobi of C in mod P is -1, that we know for sure the value is 1. Otherwise, we return value to be 1, value to be 0. Okay, that's basically what we do. Okay, so if this if statement is wrong, that means the OR statement is wrong, means both of them have to be wrong. So we can assume here it's 1 and 1. We can make it even more harder if you want to check Jacobi is 1 and the Jacobi of you can do something like, if you want to be more confident, okay, is equal to 1, and the Jacobi of C comma Q is equal to 1, because Jacobi can be 0 in some cases, right? So if you want to be very confident about this, then we set this to be 0. Okay, this should be fine as well, right? All right, so we got this idea of encryption decryption. Now we have the main function. So in the main function, I create a key size of 2048, whatever key size that's recommended in the modern days has to be used, but I will use this much smaller key size for demo purpose, 512-bit, which is not at all good, but it's fine for a quick demo. My message I'm encrypting is 1, and I'm doing an encrypt function call, right, using public key n and z, and the message is m. And then I'm asserting that when I decrypt it, I get back the same message. That's what I'm asserting. So let's run it and see what happens. Okay, nothing happens because the assertion is passing, right? So let's make a small change here. Let's just make a mistake. Okay, assertion failed. You see here, assertion failed. That's good. All right. So that means the system is working as we expected. Let's do some more changes. Let's print the ciphertext. That's important to show to you. Even though we are sending only 1 bit, when we print the ciphertext will be very large, because we are doing modular arithmetic in mod n. Remember, C is equal to z power m times x square mod n. That's why you get a very large ciphertext even for only 1 bit. Okay, that could be a problem, because if you have a very large message, you will have to multiply the length that many times. Okay, let's compute the Jacobi. If you are a eavesdropper, you're going to compute the Jacobi of C in n. You're not going to get anything useful. Let me show you why I say that. Jacobi is 1, right? But let me change this to 0. Okay, what's going to happen now? Jacobi is still 1. So because the eavesdropper doesn't know the primes P and Q, so he can't do much with it. Okay, of course, as soon as you know P and Q, you're done, and you know what was sent. So that's one thing. Now let's do one more thing. Let's just run the same thing, right? re-encrypt the same message and look at the ciphertext. I argue that the ciphertext will be different now, even though we are sending the same message 2 times. You see here, the first message is here, and the second message is here. The ciphertexts are different. Okay, that's because of encryption has randomization built inside. It randomly generates a new X every time you call an encryption function. Okay, that's good. So what is preserved in this system is the chosen message or a chosen plain text attack, right? You cannot distinguish between 2 different messages from a ciphertext alone. You can't do that because of the randomness. However, the basic version of Goldwasser-Micali has no protection against chosen ciphertext attack. You could just multiply this the ciphertext by some other number. You may be converting quadratic residue into a non-quadratic residue. Okay, just by randomly multiplying it by some number, you may be causing some problems like that. But that's something people have researched upon, so I'm not going to talk about it right now. My goal was to just to show to you that the idea of using Jacobi symbol and the legender symbol, well, when you use the composite group, it has prime factors P and Q. So only if you know the prime factors, you can compute those symbols. Therefore, the system is able to use this assumption to communicate a message 0 or 1 without being able to leak any data to the eavesdropper. So that's basically the idea of this crypto system. And I hope you got the intention of this video series. Thank you very much.